Hi guys, so we're on the next page of our guided notes. And last time we just ended with the idea that impulse is equal to the change in momentum. Now, this next page focuses on learning target number 2. So let's just read through that really quick. So number 2 says, I can derive the impulse equation from Newton's second law. And we looked at that at the end of the first video, but now let's do it again. There's multiple ways of going about it, and let's go through it step by step so that when you're asked to do this on your exam, that you'll feel confident in that. Okay, so we're trying to derive impulse. Okay, derive impulse from Newton's second law. Okay, so let's start with Newton's second law then. So we have F equals ma. Okay, so we have F equals ma, and then we also know that acceleration is a change in velocity over a change in time. That was like unit 1 or unit 2. So acceleration is that delta v, change in velocity, over that change in time. Okay, so let's substitute a into there. We're going to take what we have here and we'll plug it in for a. So that'll be force is equal to mass multiplied by delta v over delta t. Okay, so we just took our a component and we knew what a equaled and we plugged that in. Okay. Now let's multiply by delta t because it's in our denominator here, and we're wanting to get everything in the numerator. So multiply both sides by delta t. So we would get force delta t is equal to mass delta v, or velocity. This should look familiar. Force being applied over a change in time. Force being applied over a given amount of time, that's impulse. Okay, so we've started with Newton's second law and we have found impulse, and we're going to clean it up a little bit to get our final thought with momentum now. Okay, mass, change in velocity. Okay, so first we have our change in velocity and mass of an object that's going to remain the same. And delta v just means velocity final minus velocity initial. So that would be mass multiplied by velocity final minus velocity initial. Okay, I should have left some more room for this, but I could rewrite that. I could say that this force over a given amount of time is equal to mass multiplied by velocity final subtracted by that same mass multiplied by velocity initial. I just distributed that mass within the parentheses. Okay, now again we should see something really familiar here, because momentum is mass times by velocity, and that's what we have. We have mass and we have velocity, and so now we've seen again this interaction between impulse, Newton's second law, and momentum. Okay, so if this is the final velocity and then that's the initial velocity, then we can call this as a unit, this mass and this velocity, our final momentum minus our initial momentum there. So that would be what we're starting with. We didn't lose this. Impulse is equal to momentum final minus momentum initial, and final minus initial is just delta. That's the change in momentum. So starting with Newton's second law, we were able again to derive that impulse is equal to a change in momentum. Okay? So practice that and make sure that you're comfortable with deriving those equations from one another. Okay? All right, so we have this great relationship between Newton's second law and impulse and momentum. Okay, and we call this the impulse momentum theorem. Okay, that we have this interaction of the two. There's lots of different ways that we can write that, having a clear understanding of the different equations that we're working with. Okay. Couple things to keep in mind when we look at this equation. The force on an object is constant. The impulse is the product of the force times by the time applied. Okay, so when I look at this force, a constant force being applied over a given amount of time. And we know that's not usually the case in real life. Remember that graph with the softball, how the force, that interaction with the bat, it started off really small and it got bigger, and then we had a maximum and then it reduced. Okay, so we often create ideal conditions to work with certain items, so keep that in mind. And then the other thing, usually the force will not be constant, and so we tend to use an average force or that net force and multiply that by time. Okay, we can also derive impulse from a force versus time graph. We'll look at that in a minute. Okay. So far we've looked at momentum, and we have that new equation that we're working with. We know that impulse is a force applied over a given amount of time, or a change in time, and we've derived that this is equal to the change in momentum, and that is the impulse momentum theorem. Okay? So apply impulse. Why are running shoes cushioned? Okay? So I want you to take a moment and write down a couple thoughts. Using this idea, why would we want running shoes that have a cushion instead of something that's like hard and flat? And then we'll come back to that. Okay, we're going to continue with that thought, and then we'll come back to it. Okay, so we addressed how force isn't always constant, and we saw that in our graph for our softball, force over time. Okay, now something that's really cool is we can find the impulse of a situation like this where the force is changing using a force versus time graph, and the impulse is the area underneath the curve. Okay, so all this area here, and we calculate all of that, that's the impulse. We have to be careful with this, and it's not easily done traditionally, but using calculus, that's how it's done quickly, and this is not a calculus-based class. So just so you know, in the future you follow along with these skills, that's where that will come from. We can make estimates though, right? We can look at the squares, and we can do base times by height and count how many squares we have, things like that. And so by using that method and counting and estimating the best we can, from this situation, we can say that the impulse was 13.1 Newton seconds, right? Because it's force multiplied by time. Force multiplied by time. Okay, so we're going to use that in this example. So we know that the impulse is equal to 13.1, okay? And then we gain a little more information. We know that the ball has a mass of 0.145 kilograms, and we know that the initial velocity, so it's thrown with a velocity of negative 38 meters per second, and we're assuming that that is a direction, so assume that the positive direction is towards the pitcher. Let's sign this. Remember how we said that the positive x direction, we're just calling it in this situation, we're calling that towards the pitcher, right? So this is positive x direction, and then that would be a negative x direction. And let's see that. Oh, let's draw that, because it might be different than the picture really quick. Let me think. So we have Negative 38, assuming positive direction, is towards the pitcher. I think we have that backwards then. Okay, so let's change that. Let's make the negative direction like we were talking about towards the pitcher. And then when the ball leaves the pitcher, it'll have a positive velocity. And then that works for that negative 38 initial. Okay? So we know how to calculate momentum. Momentum is the mass of the object multiplied by the velocity. This is a vector quantity. The negative sign means the direction. And that's going to equal a negative 5.5 kilograms meters per second. Okay, so that is our initial momentum there. So what is the final momentum? Well, we have that impulse momentum theorem, right? So that force applied over a period of time is equal to momentum final minus momentum initial. And this is impulse. And we've already calculated that for this situation. We have this force, delta T is equal to 13.1 Newton seconds, and that the momentum initial is equal to negative 5.5? Yeah. Kilograms meters per second. Okay. So let's rearrange this to solve for that final, and then we'll plug in what we know. So we want to get this by itself, so we'll subtract that to the other side. Or sorry, add it because it was subtracted here. We will add it to the other side, and that will tell us our final. Okay. So 13.1, and we'll add the negative was considered in that, was it? Let's see, we're going to add that, and the whole thing is negative. Okay, so we have 13.1 Newton seconds, and we're going to add that to the negative 5.5 kilograms meters per second. Okay. And so that means that the final momentum is equal to 7.6. Well, that's a reasonable number. That would suggest that we've done our math right. Because what momentum it started with, it was headed this way, and so now it's positive, so it's going to be going the other way, so we anticipated having a positive there. And then kilograms meters per second. Okay. So what would the final velocity be? Well, momentum is equal to mass times by velocity, and we're going to make this final, right? And so we want to know this, so let's divide over. We know all those components. We just solved for this, so we have a 7.6 kilograms meters per second divided by the mass, which is 0.145 kilograms. Okay. Notice how kilograms are going to cancel, and we'll be left with meters per second. So we have 7.6 divided by the 0.145, 2 sig figs, 3 sig figs, so our final answer will be 2 sig figs of 52 meters per second. Great. And that's reasonable, right? When we consider the fact that we started at 38 meters per second, and then we have this interaction with the bat, which probably supplied additional velocity in the opposite direction, that the ball left the bat going faster with a faster speed than when it approached the bat.